chat how to claim post, but it doesn't work. Sorry, then it doesn't work. It asks for a password.
So, welcome everyone to the last talk of season 4. The speaker today is Alberto De Marchi from the University of München. So he is a applied mathematician who are interested in the different topic in optimization and optimal control. And now he focused on Proximal dual or augmented Lagrangian and Proximal operator splitting methods. So now he will teach us about constraint structured optimization. So now the stage is yours.
Thank you, Hoa, for the kind invitation to this webinar series and this season. And I would also like to thank my co-authors for the paper that is behind the presentation I will give today. And I've seen that Patrick Melis is also in the audience. And I know he would give a very different talk compared to mine, because I will focus on the algorithms part and on the numerical methods. And I will give perhaps less details about the analysis and the variation analysis behind this problem class. So yes, so I will give, this is the outline of the presentation. I will give an introduction about the problem class, that is this constraint structure problems, and I will introduce this proximal method for these problems without constraints, just to give some definitions and notation. And then I will move on to this problem class, and we will give stationarity conditions and investigate also sequential stationarity conditions. And then finally, we'll present a method to solve, or at least to try to solve these problems. And finally, some numerical results. So here it is, our problem class for today. So we try to minimize an objective function, which is the sum of two functions, f and g here, and we consider only finite dimensional problems in Rn. And we have also constraints that we model as a set membership constraint. So we have a function c and a set d. And why I call this problem class constraint and structure? Well, first we have constraints and structure because we have this composite objective function. And I also state here in the beginning of this slide that it is an expressive and flexible problem class. And so if you look at the assumption behind, they are pretty weak. So we assume only f and c are smooth, and in particular, they are only, the gradient is locally Lipschitz continuous. G is proper and lower semi-continuous and also prox bounded, to be precise. And then D is a non-empty closed set. So we don't assume any convexity at all here. And so we can model really a lot of different problems. And this gives us a lot of flexibility, and we can express a lot of different problems, formulations, and so on. Okay, and the motivation behind this problem class is to deal with no-smooth structures, and this has a broad meaning. And the first motivation for me was to investigate optimal control problems with switching costs. So where we have a regularization term in the objective to penalize switches of integer controls. And in particular here in red, we have this, for example, total variation, or could be any regularization that makes the control sparser in some sense. Or a different motivation is vanishing constraints. So, or constraints of this type where we have some disjunctions or some like switching constraints or either or constraints, complementarity constraints, where we have a set which is the union of some simple polytopes, and these are usually difficult to handle with the standard nonlinear solvers. So we wanted to investigate different problem formulations, so to say. Then examples, simple examples here we have that we will see in the end is a no-smooth Rosenberg's function, where we have these absolute values in the objective, and then in the constraint we have all constraints. So either of these two constraints must be satisfied. So the constraint set in this case has a strange shape, which is not easy to model using nonlinear programming. Finally, another example is a sparse portfolio where we have this S0 quasi-norm in the objective to penalize these the entries of X being non-zero. Okay, this is the motivation behind the investigation we have in this work. Okay, so here it is again the problem task that we want to analyze. But first we focus only on the objective function. So we forget about the constraints for a minute. And this F plus G problem is usually called the composite optimization problem. And we have F is smooth, at least say differentiable, and then G is proper logarithmic continuous. Okay, and to solve this problem, I focus on some kind of oracles. So what kind of information we get from this, from the data we have, so from F and G. So we use the function values and the gradient of F. And for G, we don't have a derivative. So, but I want to focus on proximal method. So I assume we can use the proximal operator of this function G, and that I will explain in a minute. And the value of this G at the proximal point X bar, what you see here. Okay, but first, what is this proximal operator or proximal mapping? So it is defined this way. So it's just a solution of another minimization problem. And we have this step size gamma, which must be positive. And here, since G is possibly non-convex, the proximal operator is a set valued. If G was convex, then this proximal operator would be single valued. But in general, for today, it's not. Now, some basic properties are that this step size gamma is a way to balance between the minimization of the G term, so our non-smooth objective, and the distance from the point X where we could compute this proximal operator. It is a way to balance the two objectives in this proximal subproblem, let's say. Then another important feature is that for many functions, we have a closed form solution for this problem. So for example, L1 norm, L2 norm, L0 norm, or many other functional regularizers, we have a closed form solution for this proximal operator. So it is usually very efficient to evaluate. And then once we have evaluated the proximal operator, it's usually also very cheap to evaluate the G at the proximal point. So that's why we have the oracles here. That is the proximal operator and the value at the proximal point. Okay, and yeah, if you look at this definition, we also have that the proximal mapping is a generalization of projections. And we can see it here. So if we define the indicator function of a set D as this function here, so 0 on the set D and plus infinity otherwise, then we have that the projection onto this set D is in fact the proximal mapping of this indicator function. Just a more complicated way to say this. Okay, so now we have these oracles, we have the problem setting. I want to give an idea how we can solve these problems. So if we denote X star a minimizer or solution of this problem, Then we have that a necessary condition is that 0 belongs to the subdifferential of this objective function at the point x star. And if so, in this setting, our setting, things are not so ugly. So the subdifferential is just the sum of the gradient of f at x star plus the subdifferential of g at x star. Okay, and we can express this also as the fact that the distance of this subdifferential to 0 is equal to 0. And we use this to define the approximate stationarity. So for a solution, we say it is epsilon approximate stationary if this condition is satisfied. Okay, different way to characterize these minimizers, these candidates, is through this proximal gradient operator. So we define this T gamma as the composition of these two steps. So we take a gradient step in blue. It's a step in the direction of the negative gradient with step size gamma, as we would do in gradient method. And then we get a point, and we take the proximal point of this, again with this step size gamma. Okay, and we say that point x star is critical for this problem if x star is a fixed point of this operator for some positive gamma. Okay, and this criticality condition is slightly stronger than stationarity and is also necessary for optimality of this x star. Okay, so now I talked about these subdifferentials, and maybe I should define them. Also, so for a function h, proper Lorentzian continuous, we have classical Rockefeller definition of regular subdifferential here. And then we have the definition of the limiting subdifferential. And what is important, or I want to stress, is this little h on top of the arrow. And that goes back to the definition of Rockefeller of attentive convergence, meaning that not only the sequence xk goes to x bar, but also the values of h at xk goes to h at x bar. And this is important in our setting because our g function is not smooth and would also be discontinuous. So we have to remember this attentive convergence to not so that our results don't fall apart. Okay, and okay, now we have the characterization of solutions, and I will move on to the algorithms. So using our oracles. So for this problem, usually we use proximal gradient method, which is a combination of proximal method and gradient method. So we use this operator I introduced before, T gamma, and it is just a fixed point iteration. So the next iterate xk plus 1 is just an element of this proximal gradient step that is set valued in general because our g can be non-convex. Okay, and we just iterate this, and we should get we should move into toward the minimizer of this Q objective. And the convergence follows from this lemma. So when we apply this operator, this proximal gradient operator, we obtain this inequality, where you can see this LF is the Lipschitz constant of the gradient of F. So you can see that if gamma LF is smaller than 1, then we obtain that the values of Q along the sequence decreases. So we obtain a reasonable method. And we can also say that this LF is usually not known a priori. And so we need an adaptive way to find this gamma along the iterations in order to obtain a minimizer, actually. So to obtain a meaningful sequence and not just some sequence. And how do we find this gamma? Well, we have to use the fact that LF is just the Lipschitz constant of F. So when we write down the algorithm, so here this is the adaptive variant of the proximal gradient method, and the red part would be just the plain proximal gradient method. So we would just apply this proximal gradient step, but we have to check if we really have this the inequality satisfied, the one I showed before. So we check on the following line if the current estimate of the Lipschitz constant is correct. So here we check this quadratic upper bound on f around xk. If this is not satisfied, then we have to make a gamma smaller, meaning, and so we try this backtracking procedure, and this will eventually stop when gamma k is sufficiently small, because f is at least locally Lipschitz continuous, so its gradient is locally Lipschitz continuous, and then we will take the step for that gamma, and then we will accept yes, the x bar k and continue to the next iteration. Okay, this is the adaptive proximal gradient method, and yeah, so the iterations are quite cheap because we have to evaluate only the gradient and then the proximal operator. And then, okay, maybe we need to check this this quadratic upper bound, but it's not very expensive. But the convergence that we get is pretty slow, so most linear. But okay, we can solve non-convex problems if we take care of this gamma. Okay, but are there faster ways to solve these problems? Well, so we have acceleration that are different types. So one is a Nesterov type, so sort of momentum on top of these proximal steps. And one famous method is called FISTA, or fast iterative soft thresholding algorithm. But usually these are applied only in the convex setting, or at least some convexity is needed in the functions to get convergence. Otherwise, you need other mechanism to ensure convergence. Different approaches: Anderson acceleration, that is sort of averaging or least squares of the iterates to get faster convergence or a faster, yeah. And a very different approach is called PANOC. It was introduced a few years ago, and this stems from the observation that the criticality condition, so x belongs, so the x is a fixed point of this operator, can be seen also as a generalized equation. So here I write in red 0 belongs to this new mapping R, which is nothing but x minus t gamma. And if you look at this, then you can say, why don't we use quasi-Newton type methods? So to get a sort of acceleration using second order acceleration, second order information. And then one can also think, okay, why don't we use limited memory to get cheaper second order estimation or iterations? And also because if we change gamma during the iterations, because we have to estimate always this Lipschitz constant and so on. Then this operator will change, so limited memory is not a bad idea. Well, this was integrated. This needs to be integrated with some sort of a globalization, as it is for Newton's method. But this also can be done using, for example, an envelope of the original objective and a line search. And then, well, this was integrated in this PANOC framework, which is nothing but this. So a limited memory quasi-Newton acceleration plus line search on the forward backward envelope. And this is also quite cheap to evaluate, so not much more expensive computationally than the proximal gradient, but can yield a superlinear convergence rate, and can also handle non-convex problems. Recently, this was also extended, so now we have PANOC Plus that can support also this F having only local ellipses continuous gradient. So this was good news for the development of augmented Lagrangian methods using this PANOC or this proximal gradient method as a subsolver. Okay, now we start with constraint structure programs. I would ask if there is any question first. No, okay, I guess there are not. So maybe I was clear, maybe I was too obscure, but I will proceed then. So we go back to our constraint structure programs here. Now we know how to solve the problem where we only have the objective function. Now we also have to consider the constraints. So again, assumptions we have behind this problem. So F and C are smooth, and here we mean that derivatives are locally Lipschitz continuous. Then G again is proper Lagrangian continuous bounded, and the set D is non-empty and closed, and could be non-convex, disconnected, or whatever. And the oracles that we use for this problem are, so we have the function evaluations as before, and the gradient for F, proximal operator for G. Then for constraints C, we evaluate them, so we have C of X, and we only use the matrix vector product when we want to have the Jacobian, let's say. So we don't need to form the Jacobian of C, but we only use matrix vector products. And for the set D, we only use projections onto the set. And or we can also use the distance in some, if it is cheaper to evaluate, but let's say we use only projections onto this set. Okay. So by this, I mean that these oracles, so we assume that these oracles are easy to evaluate, or otherwise this approach would not, maybe would not be the best to solve your problem. Okay, now we try to characterize these points for this problem. So first we define a feasible point, and it's not enough to satisfy the constraints. So C of X belongs to the set D, but we also need this point to be in the domain of our objective function. So in particular, the domain of G, which we can use to enforce constraints clearly. And then we introduce this definition of stationarity, so in the sense of Mordukovic. And so we have two parts. And first I want to say that if we consider, so if G is smooth and D is convex, then these conditions go back to the standard KKT conditions for linear programs. But in this context, we have to take care of both the G and the non-convexity of D. So this means that we have an inclusion. So we have this sub-differential of Q instead of just the gradient of Q. And then for the dual, we have multiplier y here that must belong to the limiting normal cone of D at the point C of x star. And this second part carries both feasibility, because C of x must be in D, otherwise the limit normal cone would be empty, and also the complementarity conditions, because this multiplier y must be in this cone at that point. And yeah, here we need to take the limiting normal cone and not just a normal cone, because set D is non, or can be non-convex, and so we have to look at the geometry only in this limiting sense, so around point C of x star. Okay, and we can also define an asymptotic stationarity or sequential stationarity conditions. And here it is. So we have again a lot of these sequences, and first we have to see do we have this attentive convergence for the sequence xk to a point x star, and then we have some tolerances, let's say, or auxiliary variables. So we have eta here. It is an approximation or our error for the stationarity or condition. It is the third line. Now we have ni k. It is again the error for the complementarity condition, and the last line here. And then we have to introduce also this zeta k in order to have that the argument or the point where we evaluate the limit normal cone is actually in the set D, so that the limit normal cone is non-empty. So this zeta k has to compensate for the constraint violation if C of xk is outside D, and so we can think of this zeta also as the constraint violation itself. Okay, at least in norm. Okay. Yes, and we have the theorem that if x star is a local minimizer for our constraint structure problem, then x star is an asymptotic M stationary point. So say this definition makes some sense. Okay, and now we have this characterization of the problem class that we want to deal with, and I move on to the algorithms to find meaningful candidates for our solutions. So here I write back to our comfort zone, because usually augmented Lagrangian methods are applied to equality constraints, or at least at the beginning it was applied to equality constraint problems. So we can just introduce some slack variables S here, and to obtain an equivalent problem with equality constraints. So we just introduce this equality constraint Cx minus S equals 0, and then we add the indicator of the set D to enforce that S must be in the set D. Simple. And this is again a constraint structure program itself. Okay, but it's easier to apply the augmented Lagrangian machinery. So we introduced the augmented Lagrangian function. I denote mu penalty parameter, and y is estimate of dual variable. And so the augmented Lagrangian function is just the sum of our objective function for this lifted reformulation. Then we have the inner product y with the constraint, and then we have the penalty term with this quadratic cost. And note that here mu is at the denominator, so the smaller mu, the bigger the penalization. Okay, we can use also the sum of squares to rewrite this function. Sometimes it's easier to deal with this second expression. Okay, and so now if we look at this subproblem, so usually in the augmented Lagrangian approach, we minimize this augmented Lagrangian function given some penalty parameter and this estimate y hat. So we will have to solve a subproblem like this. And if we look at the structure of this subproblem, we recognize that it's a composite optimization problem, because we have a smooth differentiable term, which is this f tilde, and then a proper lower semi-continuous term, this on the right, this g tilde. So we can use adaptive, accelerated, proximal gradient methods to solve this subproblem. And here it is important also to have a look at the gradient of f tilde. So you can see that in this expression we have that we don't need to evaluate just the Jacobian, but we just need this matrix vector multiplication to get the gradient of f tilde. And for the proximal operator of this g tilde, since g tilde is separable in x and s, then the proximal operator of g tilde will just be the combination of the two. And this means that we can still evaluate efficiently this proximal mapping. Okay. So we know how to solve this subproblem. So we can just put it in the standard augmented Lagrangian schema. So we start with some penalty parameter mu0, and we have some parameters here. And so every iteration of the augmented Lagrangian scheme is as follows. So first we select a y hat inside a bounded set y. And this is to make the method safeguarded so that our dual estimates don't blow up. And this gives stronger convergence guarantees to the method, usually. Also in infinite dimensional problems. Okay, then we select a tolerance epsilon k, and then we solve this subproblem. So we have mu k and the estimate y hat k, and we find xk and sk such that it is epsilon k stationary. And usually we should do this starting from the previous estimate, because it makes sense, and it's usually easier for the solver to find a new one. And also this should be done also for the dual variable. So y hat is usually, say, the projection of this y k minus 1 into this bounded set y. Okay, and then we solve this subproblem. We evaluate this infeasibility, zeta k, and then we compute this mu yk, that is our dual estimate. This is just a standard first order dual update. And then depending on the improvement of the feasibility of this xk, sk, then we make our penalty parameter smaller, or we keep it constant if the constraint violation is sufficiently decreased. Okay, and yeah, let's say if we, in the limit, if we want only some accuracy, we can also consider, well, we need to drive epsilon k to 0 to get some meaningful accumulation points, but we can also just take some relaxed conditions. So we just need to make epsilon k smaller than some epsilon when k is big. And we can also just ask for this implicit constraint variation to be smaller than some epsilon. So we can allow for this relaxed update criteria for the penalty parameter and also for the stationarity of our subproblems. But these are just bells and whistles. And okay, here it is our augmented Lagrangian scheme. And what does that mean? Well, so when we minimize this augmented Lagrangian, what we are doing can also be seen as a regularization of the original problem. So if we can insert here our zeta. So here we have zeta is just s minus c of x. So it goes back into the objective function. So we can replace it there. And then we can also write this without the slack variables. And we obtain that the subproblem is equivalent to the original problem with a dual regularization. And every iteration of the augmented Lagrangian scheme, we adjust the penalty parameter and the dual estimate in order to make this to approach or to make it easier. So without the dual estimate, so if the dual estimate is always equal to 0, then we will have that this is just a penalty. So instead of augmented Lagrangian, we have just a penalty method. If we also introduce a dual estimate here, we go back to the augmented Lagrangian, and we have better convergence properties here. So we don't need say in some cases we don't need mu to go to 0 to obtain a meaningful points. Okay, and we can also look at the approximate stationarity of this subproblem. And so using the definition we gave before, we just need to satisfy this condition here. So the subdifferential of this augmented Lagrangian is sufficiently close to so let's do 0, say. And I also want to give you an idea about the dual estimate update. So if we look at the differential for x, we obtain this expression here from above. And so this term here on the right is what in the approximate stationarity conditions for our problem, this is what should be just y to get the standard, say, KKT conditions for with respect to x. And so this is what motivates the dual update in the augmented Lagrangian scheme. Okay. So now we give some results about the convergence of this scheme. So and this just follows the standard results. Let's say just with some attention to deal with the set D, and the possibly non-smooth function G. Okay, so if an accumulation point of the sequence created by this scheme is in the interior of the feasible set, so here C of X star is in the interior of set D, well then we will have that the multipliers are identically 0 after finitely many iterations. That makes sense also in the standard augmented Lagrangian. And this result is quite weak due to the possibly complicated structure of the set D. But if D is separable, so let's say a hyperbox, then we will have that this result is true for every single component. So it can be refined for every single component. And another result is about the sufficient conditions to get feasible solutions, which is not always easy to have in the augmented Lagrangian or in the penalty method. So if we have a sequence where the penalty parameter is bounded away from 0, then this means that our accumulation point X star will be feasible. Another condition is that the augmented Lagrangian evaluated along these points, along the iterates, is bounded from above. So if you can bound from above, then this means that the accumulation point will be also feasible. But this is pretty standard result. And what is less standard is the fact that accumulation points here are indeed asymptotically m stationary points for our problem. So here we have to notice that this little q on top of the arrow, meaning that we need that some sequence goes to our accumulation point attentively. So not only xk goes to x star, but also q of xk goes to q of x star. And this is not trivial or automatic. And an example is given here. So we have just a one-dimensional problem. There is no function f, and we have the function g described in this piecewise way. In gray here in the picture, you see the epigraph, and so the point x equals 0 is the global maximizer in the feasible set x less equals 0, but it is not m stationary and not even asymptotically m stationary, but it is what we get if we apply our augmented Lagrangian scheme. If we start from the right, let's say, from positive x. And yeah, we get, so here on the right, you see that the iterates that we get, so x1, x2, x3, and they converge to x star equals 0, but from the right, meaning that q of xk tends to 1 and not to 0 in this case. And so, yeah, the theorem we gave before does not apply in this case. Okay, and last step before we can implement the algorithm is this is to have some elimination criteria, and we just formulate these conditions in the distance function. I'm going to hurry up here. So we just have to ask for sufficiently small epsilon k and sufficiently small zeta k to have stationarity and feasibility. And what about this complementarity? This is not in the determination criteria that we will use, and the reason is here. So we consider the proximal gradient method to solve the subproblems, but there we also use an oracle. This is how I call it, and the idea stems from this observation that the subproblem is easy with respect to the slack variables. So we can define this mapping as mu, that given x and the dual estimate, we can find the minimizer of the Lagrangian, and this is nothing but the projection of this cx plus mu y hat. So given x, so we can minimize the subproblem. Given x, we get an xk, say, then we compute an sk using this projection, and then what we will get that the minimization with respect to s is exact by construction. So what does this mean for complementarity? Well, s is this projection. We have this implication. So an element of the projection is then we have this property with respect to the limiting normal cone. So if we compare these two conditions here, and so we notice also this mu parameter is positive, then since the limiting normal cone is a cone, we have that this condition above on top here is satisfied if S is indeed this projection, meaning that if we use this projection, then the complementary condition will be satisfied by construction. Okay, so we want to minimize the augmented Lagrangian without slack variables, let's say. And so we define the proximal augmented Lagrangian using this mapping S. What we obtain is we get rid of S and we obtain the distance function here. Okay, and if we try to minimize this, where we have a problem, because this psi function is not smooth. And we can see this because here the projection D is set valued. So this augmented Lagrangian without slack variables is not really a problem that we can fit into the composite optimization setting. But we have shown in the paper, and now unfortunately I don't have enough time to show all this. It's enough just to take any element of this subdifferential and use it as a proxy for the gradient of psi. So you can just, we have an X, you can select any S in this projection, and then you can just take this expression here on the right, which is nothing but an element of the subdifferential of psi, and use it as a gradient of psi instead in a standard proximal gradient method. Well, if you put this together, then we obtain a proximal gradient with an oracle. And so the difference compared to previous method is just that these two red lines. So given xk, you select sk, so the slack variables, and then evaluate your function and the proxy for the gradient. You take the gradient step and again evaluate the slack variables, and then everything is going to work as if psi was actually smooth. Okay, and so this is this allows us to use proximal gradient methods without slack variables, and we have shown that this also works for Banach plus. So meaning that we can use accelerated methods for the subproblems without. And this is transparent actually to the solver. So this just needs to be done when you evaluate your functions from a higher level. Okay, now we have a few minutes to show some numerical results. So the first one is maybe more about a motivation, and this is about a problem with an academic problem with vanishing constraints. So the vanishing constraint has this structure: a non-negativity constraint, so x1 greater than equals 0, and when x1 is strictly positive, then we have another constraint. When x1 is equal to 0, then the other constraint vanishes. Okay, so for this simple problem, we have here in gray the visible set on the x1, x2 plane, and the global minimizer is just the origin. Just at the point, the origin, it is disconnected from the rest of the visible set. Then we have a local minimum at the point 0.05. That is at the end of this line coming out of this the polytope. Okay, and the common reformulation in nonlinear programming is just to multiply the constraints and the x1, and when x1 is equal to 0, then it will be automatically satisfied. The problem is this will not satisfy any standard constraint qualification. Okay, so we move to different formulations, and we want to exploit the structure here. So we define this set for the vanishing constraints, which is really a non-convex set. It is the union of this line and the positive orthant. And with this, we can formulate the problem in this form. So we introduce two slack variables, 3 and 4, and we enforce the vanishing constraints using function g. And with the constraint c, we just enforce that the slack variables are equal to the constraints we had, say x1 plus x2 minus 5, say, and then this just must be equal 0 to have the equality. A different formulation that we can use in this setting is using directly the set D for our vanishing constraints, and we use G just for the non-negativity constraints. And what we get is using our algorithm, using the two different formulations here. So starting from a grid of initial points on the plane, we end up only in the two minimizers. So the black dots go to the global minimizer at the origin, otherwise the crosses go to the local minimizer. So these are the results using the convex, say, formulation, where D is just a 0. If we use the non-convex formulation, we get much better results in terms of optimality. So we get much more often the global minimizer, just using a different formulation without slack variables. And this means that, or this is an example where an implicit formulation give stronger convergence results and much better results in practice. So since I think time is running out, I will go a bit faster with these other examples. And so this is just a Rosenbrock function with the non-smooth part and these OR constraints. Here we have the feasible set in gray and the contour lines. The solution is just a 0, 0. We can again formulate it using a special set for these either or constraints. We have this formulation without slack variables. And we run our algorithm. We always get the global minimizer, which is the only minimizer. And here I compare the number of total iterations, so inner iterations for the subsolver, with or without acceleration. And with acceleration, we use this BFGS approximation for the direction. And here we can see how many iterations we need without acceleration. So we go up to 10,000 or a million, whereas with acceleration, we need at most, say, most cases 100, let's say. And also we see that acceleration here helps a lot to have a more robust behavior, say, because the distribution is much narrower, around 50 iterations or so in total. And yeah, this is just a 2D problem. So when you get a large scale problem, we will need much more iteration, clearly, even with acceleration. Okay, this is the effect of the benefit of accelerated subsolver. In the paper, you can find more examples using zero norms, mixed integer obtainable problems, or matrix completion recovery problems. And yeah, but now I have to move to the conclusions. And yeah, so in this presentation, I talked about these constraint structure programs and a method based on augmented Lagrangian and proximal schemes to deal with these problems. I discussed some stationarity concepts. I have not discussed regularity or some sort of constraint qualifications, but they are in the paper. And yeah, the importance of this attentive convergence was overlooked in the literature, and we pointed out. We stressed it a lot. and also the importance of these implicit formulations for the problems, in particular, the benefit of avoiding slack variables. And we show how it is possible to solve this problem without slack variables, without losing anything from the computational side. And in fact, we have this algorithm, which you can also find online, and which is simple. So there are not many fancy mechanisms like feasibility restoration, anything, just plain simple as it is here in the presentation. We only use these first order oracles and the projection to the set, and it is matrix free, meaning that we don't never form any matrix. We just use the matrix vector product. And yeah, you can find the preprint on archive, and the code is on GitHub. It is in Julia for now, and you can also find all these examples I've shown as demos inside. Yeah, with this I would like to conclude, and thank you for your attention, and I would like to take your questions.
Thank you, Alberto, for a very interesting talk. So now it's time for questions. So if you have any questions, just unmute and then ask or write in the chat. At the meantime, while people are thinking about questions, I may ask some questions as well. Yeah, first is about the conversion result. Yeah, so when you require a point to like the value of the functions S to be in the interior of the set D, then it's then the meaning of projection now is like, I think it's not meaningful anymore, because if it's in the interior, then at some point you don't need projection.
You mean you're talking about this result, or?
Yeah, about the convergence one, when you say you need the, I think they like to satisfy some constraint qualification, something that you require a the CX star. Yeah, this one. Sorry, this one had to be interior of D, but then the meaning of then, which mean, but then you need X star. Like C is move function, and then your iteration convert to X star, which means that at some iteration that point is in the interior of D, then you don't need projection anymore. So the meaning of projection now like not very clear now. I mean, you don't need projection anymore. So do you have any strong result where CX star, are you thinking about CX star actually in the boundary of D? And then, and for the qualification, maybe use some, yeah, I don't know, some other qualifications to make sure that the, yeah.
Yeah, I have to admit I don't follow you, so I don't understand what if you're talking about this slide here.
Yeah,
this one.
Which one?
So in this one I am sharing now is the Lagrange multipliers when the constraints are inactive.
Yeah.
And this is the one where you have this interior of D.
Okay, so this one is only when it's inactive. Yes, then
yes. So it means if C of X is inside the set D, it means that the constraint is inactive. So it is not on the.
I see. But then how about when it is active, when CX star is in the boundary of D?
Yeah, when it is, then this result does not hold, and you need to use you will get. So you just have this result here. So I am a stationarity. And so the YK is usually non-zero.
Then I see. So then
yeah, this result is quite weak. I just included it. It's a standard result for nonlinear programming, just showing that you get this Y identically equals 0 when the accumulation points are, say, in the interior.
I see. Yeah. And then.
But this is quite weak result. This one.
And then the other result require the what's so-called AM stationary. So
yeah,
that one.
So I go back to the definition here.
Mhm.
And here I said that you need this zeta k to have that the argument here, so C of xk plus zeta is in the set D. Because if it is not, then the limiting normal cone is empty, or we define it empty. So you just put this zeta to have a meaningful, otherwise the last line here doesn't make much sense.
Yeah,
But then in the limit, when the points become feasible, then the zeta k disappears.
yeah, okay. Yeah. Yeah, I get it. Okay, I get it now. So like chi and zeta k is actually kind of the gap between the point CF to the distance of that to the point to the set D.
Yeah.
And when Q is continuous, then that first condition hold trivially. But then, yeah, I see.
Yeah, so when Q is continuous on the domain, then we automatically have this Q attentive convergence, so we don't have to worry about it anymore. But in the discontinuous case, it can be an issue.
Yeah, okay, thank you. And
Welcome.
any other questions to Alberto? So is there any standard approach apart from this one to this constraint structure optimization problem?
So there was an attempt a few years ago to investigate nonlinear programs with non-Lipschitz function. And in that paper, they forgot about this attentive convergence. And also there was not this set membership constraint. So it was more a standard NLP with some non-Lipschitzness. So I think this is, well, then there was a paper also with Patrick Melis about, again, an augmented Lagrangian approach with geometric constraints. So with this kind of set membership constraints, but without the composite objective function.
Okay.
And yeah, so I think this is maybe not the first one, but in the very first ones were concerning this kind of program class. I know maybe Patrick, if he is still in the audience, he can correct me, but yeah, and there are not many approaches actually.
Yeah, I think this yeah, I don't know if anyone don't have any questions, then I may ask one last quite naive questions. Have you? Yeah, so you have a thing from the chat and the questions. So can you ask the question or
There is a question in the chat.
yeah, so Liu Hai Tim. Can you ask this yourself or I will read it? Okay, they asked that I will read it. I wonder if it is possible to apply the algorithm if the function f in the objective is non-smooth, say a piecewise function.
Sorry, could you repeat, please? Yes.
But if the function f in the objective is non-smooth, say a piecewise, probably a nonlinear function.
Mm-hmm.
Mm-hmm.
So both f and g are non-convex, are non-smooth.
Just f.
But also g.
I'm not sure.
Yes,
Yeah.
both functions.
Both function.
Well, so I think the overall scheme would still work. You just need to take care how to solve the subproblems, because at that point you can put together f and g as a non-smooth term, and you need a way to solve the subproblem. If you have that, then it will work. But usually it's difficult because when you sum two non-smooth functions whose proximal operator is, let's say, cheap to compute. Well, the sum is not, usually you don't get that the sum is has a simple proximal operator. So it depends. So on specific problem, it could be doable, but very expensive. But I think the overall augmented Lagrangian approach will still work. You just need a suitable subsolver, I would say. I don't know if this answered the question, if if I understood the question, but yeah. I mean, if you have a more precise question, I can try to be more, to give a more precise answer. Yeah.
Thanks for the answer. Yeah, is there any more questions? Is don't feel annoyed if I ask this, but this one. Have you ever considered D as like, say, a moving set?
Moving set?
Like a little bit perturb of the set, like say, for a different X, say, well, I mean, for different X, they have different, like it's perturbed by some small, say, like plus alpha or something, like moving to some direction, something like that. So F is not not just a set, it's also a set value mapping.
Okay, depending on X.
Maybe, or yeah, probably.
Huh, no, I have no idea how I would deal with it. Interesting. Interesting. No, but thank you for the. This would be interesting. Do you have any application in mind, like maybe obstacle avoidance and stuff like that?
I don't know. It should. I don't know.
Okay.
I think it should. It should be useful because the way you construct the optimization, I think it's maybe applicable to some. I don't know, discrete problem or something like that, when I have to, like, on a linear, well, obviously nonlinear binary problem, something like that, like. Yeah, so.
Well, we can. So in these settings, you can also include mixed integer nonlinear programming, because with the function G, you can just put indicator or the integers. I want. The last picture of the presentation was actually to say something about this. So if I have a minute, so these are the results we got for the matrix completion with minimum rank. So we get some entries of a matrix. We want to find the matrix with those entries and with minimum rank. So if you use as objective function just the rank, you get a solution with high rank, if you just start from there. But if you use an approximation of the rank, so first the nuclear norm or Schatten P norm, and then the rank, you get much better results. Here, so you see number of iterations and the rank that we obtain. And so what I want to say with this plot is just that there is no black magic behind this. And so you can model integer problems also, also with matrices and so on, but you will not get obviously global minima for sure. But what I think is powerful is that you can do all these kind of things under the same framework. So it is really flexible. So you can play around with different objective functions with no need to use specific solvers for the rank or for a zero norm or integers and so on. Yeah.
If there's no more question for Alberto, then please join me to thank him for the interesting talk. And this is the last talk for season 4. So hope we can see each other in the next season. Thank you very much.
Thank you.